So remember that two sets have a one-to-one correspondence if you can make a perfect matching between the elements of the two sets. No leftovers, no repeats, right? And if two sets have a one-to-one correspondence, you get to say they have the same cardinality. Now, in the last section, we found out that all these different infinite sets all had the same cardinality. And that last theorem was really surprising because it seems like there's so many rational numbers. There are so many fractions packed into the real number line, and yet same cardinality as the naturals. And so it makes sense to think that maybe all infinite sets have the same cardinality, that infinite is infinite, and therefore they all match. But here's the thing, the set of real numbers is much bigger. And so the theorem I'm going to prove right now is there is no one-to-one correspondence between natural numbers and real numbers. I can't just try and fail. I have to prove that if 1,000,000 mathematicians tried for 100 years, it would never, ever, ever work. So in order to prove that it's impossible, let's pretend that there is one. Let's just pretend that we have one in our hands. And so that means that we can make a 2-column table out of it, right? With no leftovers, no repeats. And so I'll have my natural numbers on the left and my real numbers on the right. And again, this is supposed to be a one-to-one correspondence. Every real number in the world is going to fit here. And so just for the sake of argument, I'm going to fill up this table with a bunch of rando real numbers, a bunch of decimals. Here's what we need to do. We need to find a number that is guaranteed to not be anywhere on the list. It can't be equal to the 5th number, and it can't be equal to the 5,000th number. It can't match any of them. And the secret here is that if you have two numbers, these two decimal numbers, and if they differ in even one decimal place, you just thumbs down the whole thing. You say, no, they do not get to be the same real number. So here's my table again, and I'm going to start with 0 point just because all I care about right now is what's going on after the decimal point. Take a look at that first row, that first real number. Do you see how that tens place is equal to 5? I'm going to make the tens place of my magic number anything but 5. No matter what comes after in my decimal number, even if it was 949133298, blah, 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 even if every other decimal place matches, I know my number won't match the first number. And that second row, I'm going to look at the second decimal place of the second number that's on the second row. That is a 6, right? And so I'm going to make my hundreds place anything but 6. It doesn't matter what I pick as long as it's not 6. And that means I know for a fact my number won't match the second number on the list. The third decimal place of the third number is 1. I will make my third decimal place anything but 1. And we keep going down the list. I see a 0, pick anything but 0. You see a 4, pick anything but 4. You see a 7, pick anything but 7. Anything but 9, anything but 1, anything but 6. Using this process, I've crafted a number that cannot possibly be equal to any of these 9 numbers. But there's something really crucial here, or this proof doesn't work. You have to do this infinitely many times. We indicate that by putting a ... after the decimal number. Now we have to do this because we need to make sure that this decimal number that we are creating is not equal to the 10th, 11th, 12th, 13th numbers, all of the numbers that are on this list, even though we can't see them because we didn't write them down. So like, what if the 10th number on the list was 0.41260873770 and you didn't know? If you didn't have the ... if you didn't say, well, I keep making these choices infinitely many times, you might fail in this proof. So in summary, as a tidy list of steps, what are we doing to prove this? You pretend you have a one-to-one correspondence between reals and naturals. That implies that there will be a 2-column table, and the right column will have every real number in the world on it. Then, using the diagonalization process, we show that there's a real number that's not on the table. Well, does the table have every real number on it or doesn't it? I mean, what this proves is that table can't possibly exist. You can't have a 2-column table with every real number in the world on it. And so that table can't be a one-to-one correspondence, which means there is no one-to-one correspondence possible. And that means that reals and naturals don't have the same cardinality. The reals are bigger.